All right, buckle up, everybody, because today we are going deep, deep down into the Coulomb barrier.
Ooh.
It's this mysterious force that's kind of like the universe's bouncer, right?
I like that analogy.
You want to know why stars shine? How about how elements are even formed? And, okay, the big one. What on earth is stopping us from getting clean, limitless energy?
All big questions.
All of that comes back to the Coulomb barrier. And I have to say, you sent me some really amazing research on fusion reactors and what's actually happening inside stars.
Yeah, I think it's interesting to see how this one concept connects the, vastness of space and then the potential for our future here on Earth.
I know, right? Okay, so back to basics. What exactly is this Coulomb barrier? In my head, I'm picturing like a giant wall.
It's not so much a physical wall, but more of an energy hurdle.
Okay.
Imagine if you took two magnets and tried to force them together, but the same poles are facing each other.
Yeah, they push back.
Right, exactly. They push back because they both have the same charge and they just naturally repel each other. And it's the same with atomic nuclei.
The tiny centers of atoms.
Yeah, tiny centers of atoms, yeah. So the Coulomb barrier is essentially the amount of energy that they need to overcome that repulsion and fuse together.
So wait, so for fusion to happen, those tiny nuclei have to smash into each other with enough force to get over this barrier.
Yeah.
How much energy are we talking here?
Oh, we're talking an incredible amount of energy, and that's why this Coulomb barrier is so important.
I'm starting to see why this is a big deal.
It's the key to unlocking the power of fusion, not only in stars, but hopefully in future power plants.
Okay, so stars are basically giant fusion reactors.
Mm-hmm.
But we're still trying to figure out how to do the same thing here.
Exactly. Stars, they kind of have this massive advantage because they have huge gravitational pressure and, of course, temperatures that would make the hottest place on Earth feel like a freezer.
Wow.
That's how they're able to just overcome the Coulomb barrier naturally.
So we're basically trying to recreate the core of a star in the lab.
That's the dream.
No pressure.
No pressure, exactly.
So you sent me some info on two main ways that scientists are trying to do this: magnetic confinement and inertial confinement.
Right.
Let's start with magnetic confinement. I need help picturing this.
Okay, so picture a giant glowing donut, and inside this donut, atoms are stripped bare, and they're smashed together at millions of degrees.
Whoa.
So that's what's called a tokamak, which is one type of magnetic confinement fusion reactor, and they use these powerful magnets to contain the superheated plasma.
What is plasma again?
It's basically a state of matter where electrons are stripped from their atoms, allowing nuclei to just zip around with, hopefully, enough energy to overcome that Coulomb barrier and fuse.
So it's like a cosmic demolition derby in there.
Right.
So inertial confinement, that must be like the total opposite then, right?
In a way, yeah, it's more like this perfectly orchestrated microscopic explosion. So instead of using a steady magnetic field, they use powerful lasers or particle beams to compress this tiny pellet of fuel.
Wait, so they're basically making a mini star in the lab.
That's what they're trying to do.
Wow.
And again, the goal is the same, right? To try to create these extreme temperatures and pressures needed for nuclei to overcome the Coulomb barrier and fuse.
So both ways are trying to copy what happens in a star, just on different scales.
Yeah.
Have we actually done it? Have we achieved fusion here on Earth? Like, are we powering houses with fusion yet?
Not quite yet.
Okay.
I mean, we've made some huge strides, we've achieved record-breaking temperatures, and we've had fusion reactions that have lasted for, a really long time.
That's amazing.
Yeah. But there are still some major challenges, imagine trying to hold the sun in your hand.
Okay.
That's kind of the level we're dealing with here.
So it's not just about power, it's about control too.
Exactly. Yeah. Maintaining those conditions, finding materials that can withstand the heat, it's all extremely complex.
So you mentioned before that stars have this secret weapon, something called quantum tunneling.
Mm-hmm.
What in the world is that?
That is where things get really interesting, and it's super important to understand how fusion happens even in stars.
Okay, I'm intrigued. Tell me more.
Okay, so to explain it, imagine you are trying to push a really heavy box up a hill.
Okay.
In the normal world, you need a lot of force to do that.
You do.
But quantum tunneling, it would be like the box suddenly glitching through the hill.
Wait, what?
It's bizarre, but it's this real phenomenon in the quantum world where things don't always follow the rules we're used to.
So you're saying that particles in a star can cheat their way through the Coulomb barrier?
You could say that, yeah, quantum tunneling allows some nuclei to fuse, even if they don't quite have enough energy to overcome the barrier head-on. They kind of tunnel through it. And it's a key reason why stars can burn for billions of years.
Okay, my mind is officially blown.
It's pretty wild.
We've got extreme conditions, quantum loopholes, and now we're going to dive into the different fusion recipes that stars use.
Yeah, it's fascinating.
I am ready. Let's start with what's happening in our very own star, the Sun.
All right, let's do it. Our sun is this giant fusion reactor, but it's not just random explosions happening. It's actually a really finely tuned process, with specific steps. And it all starts with hydrogen.
Hydrogen, okay, that's the simplest element, right? Just
Yeah.
one proton and one electron.
Exactly. And in the sun's core, all these protons are under immense pressure and heat, so they're constantly colliding.
Yeah.
And every so often, boom, they'll overcome the Coulomb barrier and fuse, but it's not like a one-time thing.
Right.
There are multiple steps involved.
So the chain reaction.
Yeah, it's like a chain reaction, and each step has its own little barrier to overcome.
Cool.
And this is called the proton chain, and it's how our sun creates energy, mainly.
The proton chain.
Yeah, so in the first step, you have two protons that fuse together.
Yeah.
And one of those protons turns into a neutron, and that forms deuterium.
Deuterium, that sounds familiar.
It's an isotope of hydrogen, so it has one proton and one neutron.
Right, okay.
And it's a key ingredient in the next step, where deuterium fuses with another proton.
Okay.
And that forms helium-3, which has two protons and one neutron.
So we're getting closer to helium, which is the, end goal.
We're almost there.
Okay.
So the final step, this is where two helium-3 nuclei, they fuse together.
Okay.
And that forms helium-4, which is the stable form of helium, the kind we know and love, and then releases two protons back into the mix, and then the chain starts all over again.
So we're powered by, countless tiny particles smashing into each other in the sun, overcoming the Coulomb barrier every second.
Pretty much, yeah.
That's wild. But you said that the sun mainly uses this process because it's mostly hydrogen.
Right.
So what about bigger stars? What do they do?
So those larger stars, they have even more intense conditions in their cores. And that allows them to actually use a different fusion pathway. It's called the CNO cycle.
CNO cycle, what is that?
CNO, it stands for carbon, nitrogen, and oxygen.
Okay.
These elements act as catalysts in the fusion process.
Catalysts, so they're helping the fusion happen faster?
Yeah, exactly. They're like the helpers.
Okay.
So they don't actually get used up in the reaction, but they just make it go faster. So in the CNO cycle, carbon, nitrogen, and oxygen nuclei, they capture protons in a bunch of different steps.
Right.
And eventually that leads to the formation of helium and the release of energy.
So when we look up at a bright blue star, that's the CNO cycle in action, just churning out tons of energy.
Yeah. And it's a good reminder that we're all kind of connected to these huge events happening out there.
Definitely. But what happens when a star runs out of hydrogen? Does the fusion just, stop?
Not necessarily. Stars are much more resilient than that.
Okay.
Once they've fused most of their hydrogen into helium, they can actually start fusing helium into heavier elements. Yeah, this is where things get even crazier, requiring much, much higher temperatures and pressures.
So even when the core is mostly helium, the party keeps going. It just changes the music a bit.
Exactly. And one of the most important processes here is called the triple alpha process, where 3 helium nuclei fuse to form carbon.
Wait, carbon, the stuff that makes up life?
Yeah.
You're telling me that the element that's the foundation of everything, from trees to us, was made in dying stars?
It's pretty incredible, right? The elements in our bodies, they were forged billions of years ago in stars, and it all comes back to overcoming the Coulomb barrier.
This is amazing. This whole journey through stars has been, mind-blowing.
I know, it's a lot to take in.
But I keep thinking about those scientists trying to do this here on Earth.
Yeah.
Is quantum tunneling just a cool thing about stars, or can we actually use it for fusion reactors?
Now, that is a fantastic question, and it's like the cutting edge of fusion research,
Okay.
So understanding and manipulating quantum tunneling could really be the key to getting efficient fusion energy.
That's exciting. But before we jump into that, can we go back to quantum tunneling for a sec? Because it's just so bizarre. I think it deserves a deeper look.
Okay, yeah, let's do it.
Okay, quantum tunneling. We're talking about it being like a box, suddenly going through a wall.
Yeah.
But I need a little more to really get it.
Okay, yeah, let's try a different analogy.
Okay.
Imagine that you're throwing a ball at a wall.
Okay.
Now, in, the normal world, if that ball doesn't have enough energy to break through the wall, it'll bounce back, right?
Right, obviously.
But in the quantum world, there's a chance that that ball could tunnel through the wall and appear on the other side.
But, how is that even possible?
Well, it all comes down to this idea that particles at the quantum level act like waves.
Okay.
So it's kind of hard to picture, I know, but instead of thinking them as tiny balls, think of them as like waves, and waves can do some pretty crazy things.
Okay, I'm picturing like a wave crashing on a beach. Sometimes the water goes around the rock, sometimes it goes over.
Exactly. And in the quantum world, there's a chance that a wave or a particle can kind of spread out and extend beyond a barrier, even if it doesn't have enough energy to go over it.
Okay.
And if part of that wave ends up on the other side of the barrier, then there's a chance that the particle will just suddenly be there too.
So it's like the particle is playing hide and seek,
Kind of, yeah.
and it could just pop up wherever.
And the craziest thing is that it's not just like a theory. Quantum tunneling has been observed in labs.
Oh, wow.
It's happening all around us. We just can't see it.
So this is what's happening in stars. Like some of those nuclei are tunneling through the
Well-
Coulomb barrier. They're fusing, even though they might not have enough energy to do it normally.
That's exactly right. And that's a big reason why fusion is possible in stars in the first place.
Wow.
Because without quantum tunneling, it would be so much harder for those nuclei to overcome the Coulomb barrier and fuse.
This is incredible. So if it's happening in stars, does that mean we can, use it to our advantage? Could we change quantum tunneling to make fusion reactors better?
That is the million-dollar question, and it's something that researchers are working on right now.
Wow.
It's a whole new area of fusion science. They're looking for ways to enhance quantum tunneling, to kind of make it more likely to happen.
So we could use, quantum tricks to make fusion easier.
Yeah, potentially. Imagine if we could design reactors that take advantage of quantum tunneling to lower the energy we need for fusion.
That would be amazing.
Yeah, it'd be a game changer.
It's like we're learning to speak the language of the universe.
Right.
We've gone from imagining pushing magnets together to the world of quantum tunneling, and it's all connected to the Coulomb barrier.
Yeah, and it just goes to show how understanding the universe, even the tiniest parts of it, can have a huge impact on our future.
Totally.
I mean, the quest for fusion energy, the elements that make up our world, even how stars shine, it all goes back to this barrier and how we can overcome it.
I know, it's mind-blowing.
Yeah, I think the takeaway here is that we are a part of this amazing cosmic story, The atoms in our bodies were created in stars through these processes that rely on overcoming this barrier, and now we're trying to understand those same forces to make a better future here.
It's pretty humbling, and it kind of makes you think, if quantum tunneling lets particles kind of cheat the system, what other impossible things might be happening at the quantum level, What else is out there?
It's a great question, and that's the beauty of science, right? There's always something new to discover, always more to learn. This deep dive was just the beginning, and who knows what amazing things we'll find next.
I can't wait to find out.